So, welcome to this lecture, Machine Learning. Welcome to this course. My name is Steffen Stab. I'm professor for analytic computing from the Institute for Artificial Intelligence. And I'll give this lecture. There are a whole range of PhD students and postdocs who help me giving the exercises. And there will be different tutors who give exercises. So we have a large team to help you with the content. Today, I want to tell you a little bit what this course is about and what it's not, and some of the formal requirements. And so you should know what the course is about, what are some example applications, also some very basic terminology that we will encounter today, and understand a few differences. What may be noteworthy for you and maybe share with your colleagues, this is the last time we give this course as a master course, because as of next summer term, we will do this as a bachelor course. Of course, we will adapt it a bit, leave away a bit of the mathematics. Of course, when you want this to be examined as a master course, you will not be able to repeat the course next year in the summer term, because then it will be a bachelor course. I mean, you're happy to join and attend the lecture, but you will not be able, if you need it as a master course, to attend the examinations next summer term, right? So just that you're aware of that. Of course, if people fail for whatever good reasons, we will still have repeat exams or maybe some oral exams, but you must know that this is the time to do this as a master class in machine learning. Having said this, the main motivation is that we introduce students earlier to machine learning, already during the bachelor studies. And we have a number of master courses right now, reinforcement learning, probabilistic machine learning, that happen in the winter term. So there will still be offers in machine learning and, of course, in seminars, in projects, etc., etc. And so there is a bit of more of a time to pick this up in the bachelor and continue with it in the master. But maybe for you that's not that relevant, because then you hopefully have done and passed this all successfully. Then we're all most happy. This is a master course. That means we have certain expectations that you can program, that you know linear algebra, calculus, probability theory, because you need this here, that you can read, understand, and write mathematical formulas, right? It's also, it doesn't include deep mathematics in the sense of proofs, but some of the formulas you need to get used to them. They are also repetitive at some point, but it is important to understand them, to be able to understand the papers that you might eventually read for your master thesis. This course is a little bit awkward because of an awkward history. So awkward in the sense that there are a few data science students. Where are you? Who is a data science student? Thank you very much, who attend this course already as a bachelor course. And then the exam is slightly different. There's a separate exercise only for data science students. And there is always confusion every year that this is a special group and they have their exercise session and their exam. And all other bachelor students, no matter where they come from, if you're not a bachelor student in data science, you belong to this second class, because you take this course early. Well, I mean, this is allowed. You can take master courses to some extent in your bachelor studies. But when you do so, you count automatically as a master student, and you don't belong to this first group here. And then the master students come from different computer science subjects, simulation science, cybernetics, you name it. And also engineering students and engineering scientists. I want to emphasize that it's a course for master students, and that, of course, has implications on the foundations that we expect from you and on the foundations that we expect from you, for example, with mathematics. We cannot really accept complaints if you don't have the required knowledge, right? The data science students have a different track, so this is less of a matter, but we had from time to time complaints that people said, yeah, but I don't have enough basis in this or in that. As a computer science major, you should have that, and that's the yardstick that we apply. But of course, you're a master student, and you're a master university student. And the good news here is we expect that you can familiarize yourself if you have some gaps in your knowledge, right? You're not in high school anymore, so I'm sure you can do very well. Who visits this course in the past? This was from the evaluation of the module, and this was just like 40 out of I don't know how many people who visited the course then actually gave feedback, and these were the courses where they came from. So broad spectrum. And nevertheless, the yardstick is Master of Science in Computer Science. We have this ISA program, and we try to support engineers to the extent that it's possible for us. Having said that, we had in the past cases where an engineer came, especially in those engineering subjects that were further away from programming and mathematics, and then complained that he couldn't follow, right? So I appreciate if you're here and take the extra effort, but at the same time, the yardstick is not an engineer, let's say in civil engineering, but the yardstick is the master in computer science. Just we get the expectations right. ISA tries to support specifically, and I come to that in 2 slides, I think, when I explain the specific exercise classes. I will record lectures. Please apologize if the lectures are not readily available after the class. This has technical reasons. When I go to my office after this class, I cannot immediately push the button to process it because it's still processing. At some point, I have to push the button, and then it starts processing for several hours. And then have no clock set up for the middle of the night to then push the button again and publish it. And then if I'm busy with other stuff, then I sometimes even forget it, and it takes 2 days. Because there is really always requires the pushing of button with several hours in between, and that's not necessarily the thing that I think about day and night. And so please apologize if that takes a bit longer. It cannot be reduced to a minimum. Submit your exercises in groups of 3. The exercises will include pen and paper as well as programming exercises. Check out the details of how to submit and hand in the exercises. There is also a forum. You can try to find other people with whom you can submit your exercises. All the details will also be explained in the exercise sessions. Then you need to acquire admission to exam. So we set out some criteria, and this is the prerequisite such that you can enter the exam. Once you have acquired this permission to enter the exam, you can also do it at a later point in time. Because it is only offered this year, do not delay it, please, right? Of course, there will be a resit in the spring break, but please do not delay it. I think that would be most convenient for you if you can do it immediately. Pass the written exam. That's typically happening in September and March. For September, we still look for a time slot, maybe even late August or something like that. The first time slot we were allocated, like in the last week of September, doesn't work technically. And so we'll still wait for getting the assignment centrally. It's done centrally because we need several lecture halls to do the exam to allow for enough space. I'm asked this very often, especially by exchange students, and I understand their problems that exchange students typically stay only here until end of July, but I cannot offer additional exams. It just doesn't scale with so many people. And so that's my apologies. There will be just one exam for everyone in this summer, which will at the yet to be specified point in time. Yeah, so look out for this specific point in time. Watch out for the lecture material and exercise materials on Elias. So I uploaded the slides that I show here this morning, and the lecture recordings will also be there. The exercises for the master students of computer science, informatics, software engineering, etc., as well as also the people who have elected to take this course, are in this exercise class of Elias. The data science students have their own separate exercise class, which is only for them and runs by this name. And then I said we try to support engineering students. We have currently, only this year, some funds to do this. And for engineering students, there is a specific exercise. However, now the question we run into is, I'm a cybernetics student, am I an engineer? So we have only at most 30 slots for this class, and typically we have more than 30 students coming from engineering if we include, for example, cybernetics. So the way we do it, feel free to apply with and including your subject, and then we will prefer those students whose subject is further away from computer science for this specific class. What we also have there are additional materials, pointers to please go here to learn something about Python, please go there to read about probability theory, etc., to make life a little bit easier for them. It's limited to these 30 cases, so again, taking my favorite example from the cybernetics, they learn, well, maybe not the full program for programming, but at least a bit. And they do a lot of math, so they typically don't need this specific exercise. Then we have another one by additional money, so not in the usual curriculum, which is for engineering scientists. These are only people who currently write their master thesis or PhD thesis. And this is like the special program from the AI Software Academy for people who bring their own project. And what we try to do with a small number of people is to map the content of their project to the lecture. And so this is not meant for those who just want to attend the lecture, get a credit for the lecture, but rather for people who bring their own project. And it's small difference, scientists versus students. So the scientist means you have your own scientific project that you bring to the table. If there's still some shadow of doubt, please ask me or the people who run this. So this is Tim Schneider who runs it, and Osama Mohammed who runs this one. But I hope the overall delineation should be clear. Any questions on this? Okay. You should go this one here. Yeah. Okay. Our communication should happen all via the Elias forums, which are available in the exercises. Couldn't figure out this morning whether, I mean, this is for the forum. in the big group of exercises, we still have to figure out whether the data science students and the others attend the same forum or a different forum. The idea is, as soon as you ask any question about the content of lecture or exercises, go there. We will ignore all personal email. Why? If you have the problem, then other people will have the problem too. So we don't want to answer this as an email. Please go ahead, specify. If you find a mistake, please put it there. We do mistakes. If you find them, extra praise for you. And put them there, and other people may stumble over the same problem and will benefit from the clarification. If a colleague posts a problem at 10 p.m. at night, and you happen to read it at 10 p.m. 5 and know the answer, please answer, right? So you don't have to wait for us if we're not online at that time. And we will not be online, of course, 24/7. We have a few other jobs to do also. If you have something which is specific, for example, includes specific personal data, then of course, by all means, send us email, right? If you say, I'm not sure, yeah, so your question might specify as be warranting a personal email perhaps. But everything that involves personal data, send us a personal email. Everything else, share on the forum. Some hints about how we proceed. I do this lecture, I share the slides, I share the lecture recording. However, these slides are not a script. I sometimes scribble things on the blackboard. I don't mean it to be a script. I want that you participate actively, listen and take notes. Whatever form you do. Not everything that I say will be written down in some way. So take notes. Of course, you can go back to the recording of the lecture, but it's an enormous effort to go back to particular places. Yeah, and to re-watch the whole lecture once you prepare for the exam is always an enormous effort that you probably don't want to do. So take notes. I know that most people sit there passively, and for me personally, when I attend meetings and I don't take notes and I don't have an active role, I know that I feel drowsy after 10 minutes and tend to fall asleep. So take notes, not to fall asleep. What do we want to achieve in this course? You should know the basics of machine learning after this course, hopefully. Core assumptions for me are mostly what goes in, what comes out. As funny as that sounds, I ask many students this question, what goes in, what comes out, and they cannot answer it. I mean, this is what you need to know about an algorithm primarily. What is the input, what is the output? If you don't know that, you don't know the algorithm, no matter what else you tell. So, assumptions, what comes in, what comes out. Now, then of course the methods, how do they work? Not only how do they work, what are the steps, but why are they composed the way they are composed? What's the underlying mathematical rationale? There it also gets hairy. So people tend to focus on the steps, but they tend to ignore like the simple things like input-output, and they tend to ignore the complicated things like what is the underlying rationale for why the steps are done like they are done. And then people often like to have a kind of a recipe. Now where's the chalk? Here. A recipe which is a bit structured like an XML document. Like step 1, step 1A, step 1B, step 2, 2A, 2B, 2C, and then we can go method by method by method. That's how many people want to have the lecture. That's not what I want you to learn. What do I want you to learn? that there are different methods. Method 1. And these different methods have common assumptions, common rationals, common problems. And so a lot of what applies to the first method also applies to the second method, even if that method looks completely different. Right? Problems like overfitting, regularization, things that we will talk about, we may introduce with one method, let's say linear regression, and then they also apply for neural networks. They have similar problems, and quite often the second method is being modified in order to address the problems that the first have. So what I try to do is I try to wander through these methods and also do such other kind of path. And you should understand how the same kind of problems, topics, assumptions apply to the different methods, because it is interconnected. Okay, then of course you need to master the theory, the mathematical formulas, and in particular the reasons for why they are as they are. What do we also want to achieve? We want to achieve that you have a little bit of experience in implementing machine learning solutions, so you can solve some problems with machine learning algorithms. So get your hands dirty, and yeah. And now some people say, but then, oh, not everything what you ask for here is actually tested fully in the exam. That's right. I mean, we sometimes do some programming question in the exam, but it's quite clear. Having these programming questions in the exam is always a bit of a crutch. It's never quite a good way to test your competence in actual programming. So we have the exam, but we want you to learn more than just what you need to pass the exam. For example, get your hands dirty on dealing with some data, even if that's not directly tested. People have complained in the past, but this topic was not tested for in the exam. That's not necessarily required, because the learning goes beyond just what you need to pass the exam. Well, and I've emphasized it again, there's this famous saying by Ludwig Boltzmann, nothing is more practical than a good theory, and so this will also be emphasized here in this talk. This may, in turn, actually be a little bit different in a bachelor course, where one may emphasize the more practical things a little bit more. What is also important to understand here is that if you don't look for deeper understanding, but just for memorizing long formulas, you will never succeed. People try sometimes to do this, that they just try to memorize all the content on the slides. And they always fail because it's too many. And formulas can be long. This is the disadvantage. The advantage is these formulas are not always different. They overlap to a large extent. And so in terms of meaningful entities, the variety is actually limited. There is literature. I especially recommend the Probabilistic Machine Learning. It's a book series, so it's a lot more content that we can address. I think it's now 3 books, and each of these is a thick book. So it's far more than we can handle. When we teach the material, very often people say, but here in this book is it written like this, here in this book is like that, and this video lecture I found on YouTube does it like this. And I have to say, we don't care. Because, I mean, really doing all this mapping takes quite a lot of time that we leave to you. If you have a problem with understanding it and aligning it with the probabilistic machine learning book, then I'm willing to do this, to go this extra mile, so that you have one point of reference. And we don't follow exactly its notation, right? Actually, we did this class, and only after that the book came out or was available to us. And so we're happy to help you with aligning with the probabilistic machine learning book. We will not align with anything else that you find somewhere out there in the depth of the web. It's just requiring too much time, okay? And by the way, these links are also PDFs that you can download for free, so I think that's also quite nice. So it will be a longer source for you. I think one book is not downloadable, but I think we don't need that. Okay, there are a few hints for what are the kind of conferences where you might later on find stuff for a seminar or a thesis. I would not say that there wouldn't be nice visualizations around. For example, here are some pointers which I encourage you to look at if you like. Some people think more visually, and that's perfectly fine. And then these additional materials may support you in your learning of the material. But obviously, we cannot adjust everything. Machine learning has exploded. I mean, to each of these conferences, people will now submit about 10,000 papers every year. So these are just 4 conferences. These are 40,000 papers. A quarter of them is accepted. These are 10,000 papers per year. So if you want to keep up with 10,000 papers per year for which you need 1 day to read a single paper, the year is too short. So also don't be disappointed if we will not be able to answer everything about machine learning that you can ask. Feel free to ask, but it's a broad field. It's a really exploded field. Okay, so far, any questions? Okay, no questions up to this point. Now, why do we do this lecture? We do it because of the success that machine learning has achieved in the last 20 years and made possible applications that would not be thinkable without machine learning. And some of the stuff that we dream about, like autonomous cars, date back, well, 19 years. Like this is a photo of Stanley. This was the first car that autonomously drove through the desert. This was a DARPA Grand Challenge. The first year they did it in 2004. None of the vehicles arrived. They all got stuck in the desert. In the second year, there was actually a successful team. Actually, it was not the first autonomous car. The first really autonomous car was actually by Ansel Dickmann from the Bundeswehr-Universität Munich, which was done in the 90s. Yeah? But the really one that made people, and they used a small bus because they needed to somehow integrate the computers, which were larger at that time. But the first real one, which also heavily relied on machine learning, run by Sebastian Thrun, originally scientist from Bonn and Hildesheim, who then became Stanford professor. He and his team won this desert, 150 miles through the desert. Another example, Watson in 2011 won a game show. And this game show, people, here are some world champions in this game show, were asked questions like, Harriet Boyd Hawes was the first to excavate a Minoan settlement on this island. Now the question to you, which island is meant? Who knows it? There's one hint that you might perhaps, if you have visited it, I would not have been able to answer either, right? So, but actually, if you visited Crete, you might have visited the Palace of Knossos, and they also talked about this Minoan culture there. But so this is the kind of question that these champions were about to ask, and the Watson, IBM Watson, then bet these humans who were particularly good at answering such kind of questions with also such kind of complicated sentence structures. So here, Watson was sitting in the middle. Well, of course, more like a depiction of it. Or translating text to speech, right? We are sort of like now used to that. People still optimize that to make it more naturally sounding with more prosody, et cetera, but it works. Translating texts, of course, I use DeepL a lot. Skype does it for speech. Image classification. So this was actually around 2011, 2012, when people decided that neural networks were the next big thing, because people had looked at classifying objects in images for a very long time. Computer vision is an old discipline. And they didn't come very far, one has to say. And only in 2011 or 12, I don't recall exactly, people managed to actually achieve human-like performance on the task of recognizing dogs and cats and small here toy ducks in these pictures. And there was a reason why it was not possible before. Actually, the algorithms were quite old. The algorithms dated back to the 90s. But what was new in 2011 were two things. Compute power was available in a different scale than it was 20 years, 30 years before. And people had used the World Wide Web, the internet, to collect example images. And so building a huge database of classified images was core to learning from data what made a duck or a cat or a dog. And then, of course, it didn't stop there. So at 2015, they achieved human-like performance. Later on, superhuman-like performance, where superhuman has to be taken with a grain of salt, because they are very good at doing this classification where humans get bored. I mean, imagine you have to classify 10,000 of these images, yeah? You would do the first 10 with a lot of energy, but after 3,474, I'm sure your energy has waned a bit. And so you do mistakes. And so the computer doesn't do these kind of mistakes. The computer does other kind of mistakes. It learns funny things. For example, it learns that a husky is described by snow in the background. Now, what happens if people bring huskies here to Germany, where there's not much snow, not their natural habitat? Dogs may not feel very comfortable in the summer heat, but you should still recognize the husky, right? No problem for you, but it's a problem for the typical machine learning algorithm. In 2015, a friend of mine from Rensselaer wrote a book, and he was in the middle of the writing, approaching the end, and he had a chapter that Go would be a game that would be impossible to play for artificial intelligence, like for the next 10 years. And like a few months later, AlphaGo brought out, I'm not sure the name of the company is Alpha something, was later acquired by Google. They brought out this AlphaGo game, and that was able to beat a grandmaster of the game of Go. And what is the problem with the game of Go is you have this field, I think it's 19 by 19 many places, and whether there's a black or white or no stone at a particular place gives a different game. And all the existing game playing strategies didn't work because the combinatorial explosion after just 2-3 further moves was just too big. The branching space, you can initially place your stone into almost 400 different places. This is a branching factor. When you multiply this 3 times, you very quickly have a very large search space. And only when AlphaGo tamed this huge search space, here's a search space possible states for Go, 2 times 10 to the power 170. Compare that to chess, 10 to the power 46. So this is a huge difference in the number of states that you can a priori consider. And only when they found a way to tame this by recognizing patterns, also with neural networks, and by doing reinforcement search, reinforcement learning was important for that, they were able to conquer this problem of playing Go successfully. Now, over the last 2 years, 3 years, what has become very prominent, of course, and I think everyone knows about that, was generative AI, where the machine learning algorithms learn directly from the data about the data. And applications like DALL-E then allows to learn from such pictures of koala bears and pictures of motorcycles. And then you can ask it to produce a koala on a motorcycle. And it does so, like this or that, or you see, so the algorithm has learned some characteristics of what constitutes a koala bear, what constitutes a motorcycle. It doesn't always work out fully. I mean, these engines are also known for doing some stupid mistakes, like providing people with 6 fingers instead of 5 or only 4. Of course, there are people who have 6 fingers or 4, but it's not the average. And yeah, you can try. Last year I tried, I didn't try again. I should probably have tried again. Show a professor in a red sweater teach machine learning to a class of 400 students, and that was the outcome. Some gibberish in the background and something that looks somewhat Greek, but not quite. So you see, but of course also these get better and better, and deep fakes get better and better up to a degree such that you can now talk with anyone's voice, and which is also a little bit frightening, one has to say. ChatGPT, I think I carry coals to Newcastle or owls to Athens when I talk about this, so maybe I just leave this. You will all know this, maybe some of you use it. I also encourage my students to use ChatGPT, but to use ChatGPT for improving their content. Don't rely on it for actual content, because it just fantasizes. For example, you ask for the age of Steffen Staab, it always makes me older than I really am. Yeah? So don't trust it. I can show you my birth certificate if you don't believe me. And so factual statements are plain wrong, and it may also suggest a lot of stupid stuff. But if you tell him, okay, I have a paragraph formulated like this, please write it in a more formal manner, in better English. It's pretty good at doing this kind of improvements. Yeah? By the way, ChatGPT has made our lives harder in the sense that originally, if a student was really lazy and did not put effort into a seminar work, you would just even look at the first 3 sentences of a text and you would spot it. Now it's harder because of ChatGPT. People use it thinking we will not spot it, but of course we do. Right? I mean, if there's no content, ChatGPT will not produce meaningful content for you. Even if you think, oh, that reads nicely, yeah? It is just no content in there. At least, it seems that maybe some subjects in the, I only can say this if there are no people from the humanities here. So in the humanities, sometimes people can play this over, but unfortunately, in the natural and engineering sciences, you cannot replace content for gobbledygook. So even if it reads well, it will probably have no content. Don't try it. We'll find out. But I agree, it's more work for us to find out. But we'll do. By the way, people, of course, use also ChatGPT and Copilot, GitHub Copilot, to do programming. And again, it can speed up your work, but without understanding, it will not really produce the right kind of code. It's good at doing the simple cases. Doing simple things quicker, that's what it's good. But it does not solve complicated problems for you. And we are interested for you to solve complicated problems, because why should you learn the simple stuff? You will be replaced by generative AI. You should rather learn the stuff that's difficult. That's where, for the foreseeable future, AI will have a hard time to replace you with your expertise. Here's another example of generative AI. PaLM-E, it's also already like a year old. And it does not only include pictures and text, but it also combines movements. So with PaLM-E, people have trained him to say, pick up this out of this drawer, or move this box to that on top of this red block. And so by giving, for example, text instructions, the robot has learned to put these text instructions into corresponding activities. Of course, the text instructions are still rather simple at this point in time, and it will still be a major obstacle to do complicated stuff. And complicated stuff often means what is easy for humans is hard for AI, and vice versa. So what is hard for AI, for example, is pick a grape without squashing it. Yeah, that's a difficult task for an AI, and which seems like too simple. So even a 3-year-old can do it, and AI is still really bad at doing it. Okay, so this was now motivation. I have to say also that in this course, we will not treat any of these applications, because building an application is done with a huge team, and before you can do any of that, you need to understand the basics. Yeah? So this is sort of like always in the background, and for example, we have this lecture on foundation models that we do in the winter, where we talk about ChatGPT and the likes, and again, the basics of ChatGPT, which we also not have here in the lecture, but we build on the content here to be able to talk about how to learn foundation models that are used for ChatGPT, DALL-E, PaLM-E, you name it. Or Matthias Niebert gives this lecture on reinforcement learning, which is core to all kind of robot tasks. So this is, from your point of view in this lecture, still a bit far out, but trust me if I tell you that what we do here is required so you can solve these more complicated tasks. From scratch, I mean, just using something that's already finished and then changing a parameter is not solving a task from my point of view. So having this in the distant, what is now the immediate task that we have to solve in machine learning? Okay, what I've said before, you need to specify what is the input, and you need to specify what is the output. So as input, we typically have data. And output, what we want in machine learning is always a more compact description of the data. So sometimes some people understand machine learning also as a task of compression. Actually, there are workshops at the big conferences that relate compression and machine learning. And how can you compress? You can do this for different purposes. You can learn to predict. So, for example, you go to the supermarket, you place some fruits or vegetables on this scanner, and it recognizes this is apples, this is pears, this is strawberries, and weighs them, right? So for this, it needs to classify what the product is, to classify and say, this is apple, this is a pear, this is an orange, and then be able to calculate the correct price based on the weight of the fruit. This is classification. You can also try to predict some value, right? So you can try to predict from some observation what, for example, a steering angle should be for a car in order to keep the car on the lane. This is also kind of prediction task. And well, if you veer more to the side, you have to veer stronger in the opposite direction, and always predict continuously the value of how much the steering wheel should be turned. You also want to represent, you learn to represent. What is the problem with learning to represent? How would you describe such a bowl of fruit? How would you do it? But how do you describe the container? Shape and colors, okay. Words, yeah, right. Okay, so these are some of the ingredients. Now, what does the computer have as input data? It's pixels. And now the big problem is, how do you get from pixels? Well, here, this brown is a different brown than that over there. So just having brown is not entirely meaningful. Whether it's the same brown all over the place or here it has some texture makes a difference as to regard your prediction of material. Right? Or there are these apps that try to predict you scan it and they predict how much calories intakes you will have for some dish. Yeah? You need to predict, and to turn this into a meaningful prediction, could be brown, could be the shape of a bowl, could be whatever. So learning to represent what you see is the task of turning this into features that can be used for classification or regression or other tasks. So this is now actually a very big task, learning what is a meaningful description. And it's not straightforward. And actually, when I told you that people have looked at object classification since the 60s until the late zeros and didn't achieve it, they always built these features manually. And they were not successful at achieving a good quality prediction. Also using machine learning, but it was still not good enough. Okay, so you try to learn to represent what you have in front of you. And this is actually the key success also from the last 15 years in machine learning, that you learn what features matter and you don't impose it on the system, you learn it from the system. And you use it also to describe and understand. Now, sometimes you have data and you try to understand. You have customer data. You try to understand what's your customers made of, right? So, for example, one customer may have a big family, like 6 kids. The other customer is a student. The next customer is a pensioner, et cetera, et cetera. So understanding your target groups and then maybe addressing them in different ways. This is also a way of reducing compactifying data. Okay, so input data, output a more compact description for different purposes. And we will look into methods for doing that. What I want to mention also already here, machine learning has downsides. What are some downsides? Well, the first one is environmental. A very old system which underlies many text processing tasks, that's called BERT. And this is a very old number. I should have tried to look up a newer number. Training this BERT, which was a small system compared for nowadays systems, produced 284 tons of carbon dioxide just for training this one system. Now, ChatGPT 4, etc., orders of magnitudes more than that. And when you read in the news, the larger compute centers that the big AI companies are planning will multiply that again. It's the number of parameters that are used in the system have risen into the trillions. The environmental problem doesn't grow quite as fast because the chips become more energy efficient, but still it is a huge toll on the environment. Then inequitable access. So some countries are rich, others are rather compute poor. So you could say, okay, US and China, they have massive investments in compute infrastructure to produce these very large representations for ChatGPT, DALL-E, etc. Europe has a bit of it, but not to the same extent. And then if you look for Africa, they are very far from being able to catch up with that. And that, of course, means also that when AI is used, the pictures that are ingrained in the corresponding cultures are pushed forward, and others are not advanced. And what is the problem, or one problem with that? This is a harmful bias that may arise. And just one example for this harmful bias is a rather old one, I think 8 years old or 9 years old. Google offered the possibility to do automatic classification of pictures, and also now photo software does that. And then a person complained because two of her friends were classified as gorillas. So this is this now infamous picture here. And obviously the data provided was not sufficiently indicative to train the classes of dark-skinned people and gorillas. And at least at that time, I'm not sure what's now, but at that time, Google was not able to solve the problem with the data they had. So they decided not to classify anything as gorillas as a kind of a post-processing step. Maybe they solved it now, I wouldn't guarantee for that. But, and of course, no one intended to behave badly like this. There was no poor intention behind this, but just because of the data that was available for training and the procedure, the problematic outcome has arisen. There's also other lack of safety. Full self-driving cars still not around the corner. Yeah, I'll have one rather recent car, and it gets confused by the yellow and white lines at construction sites, so I wouldn't trust it to do full self-driving, as its makers claim it could do. Machine learning is tested a lot for clinical problems, for medical problems. But there is not much use of machine learning in clinical practice, a little bit for discovery of skin cancer. So that works pretty well. But in many other places, it remains very challenging to imitate what the medical doctor can do. People look at ChatGPT and have the impression, especially on first sight, oh, this looks really nice. But you also have to understand what it's doing is it's digesting data, it's learning statistics, and it uses advanced statistics to produce content. So one way to describe this is that ChatGPT is a stochastic parrot and not a mechanism that reasons about what it sees and to think about what it sees. So it's clearly also overrated by some people, at least for some purposes. But that's the same problem I mentioned before, right? It doesn't produce seminar work. It only produces sequences of words that almost look like seminar works. One side note, we have also one initiative here at the university which involves different faculty over the different departments to think about the intelligent systems, to reflect about their shortcomings. And people look at this from different angles. For example, there are junior researchers from psychology, philosophy, computer science, computational linguistics involved in this initiative. To give you a few hints of what we are doing, for example, we have some joint work with companies like Bosch or Mercedes. So this was a master thesis that Thomas Monninger did at Mercedes. He's now a researcher there and doing his PhD with us. And they look into self-driving cars and understanding traffic situations. And so what you try to do is you try to understand these objects and what these objects do or plan to do. So here you try to predict, is this a parking car, or will this car maybe go again when this traffic light becomes green? And of course, depending on what the estimate is, you think about overtaking or maybe waiting for the car to move left. Likewise here, you have some problem on the street and the police were waiting here and you try to find out, predict whether you should move on slowly or not at all, depending on its behavior. We also look at applications. I mean, oftentimes I have to say we don't care about the application as much as about the algorithms, but of course, testing the algorithms always has to happen in the context of some application. And one application here is classification of some tissue. And one of our PhD students, Bo, he worked on classification. So you try to classify cells. And we use background knowledge in so-called ontology. In an ontology or taxonomy, you have background knowledge how different cell types are related to each other. And in addition to the data that comes from samples that you see, and the sequence data, you also use this background knowledge in order to have a classifier. And this classifier can not only tell you it's type A or B or C, but it classifies as it's type A, but of type 47, and so has multiple classifications involved at the same time. One PhD student is from another company, and he looks at anomalies and tries to find out from data if new data is coming in, is this now within the expected behavior or is it outside of the expected behavior? What you also should always be aware of, there's no one solution for every and all problems. So even if I say try to catch this behavior, whether it's normal or outside of the expected, people build different kind of machine learning architectures for all kinds of different applications because the characteristics are different, the data are different. And what you always need to do is you always need to understand the data. The worst thing you can always do is to have a problem, throw machine learning at it without looking. Yeah, you should always look at the data first. And we also work with language models. This was one example where the problem was to have here a hierarchy in this bioinformatics domain and a knowledge graph also in that domain, and they use different types of terms. And we use, for example, language prompting, so asking ChatGPT, Llama et al. In order to find the alignments between the different hierarchies. And well, maybe if this lecture is relevant to, interesting to you, at the very end you might be interested to discuss some opportunities for thesis or projects, and we have some website where we have a current list, but you can also talk individually to PhD students, postdocs about specific topics. Okay, so far, yeah? What kind of students can write a thesis in our group? Well, it depends basically on for which students do we have the right to supervise the thesis. Obviously, computer science, software engineering, media informatics, etc., all that falls into our domain for which we have the rights to supervise thesis. For things like autonomous systems, was one example. We don't have the right immediately, but we collaborate with them so often that we sometimes do it and then have another colleague from this field. And if a field is very far away, that one would have to check, and you need a formally separate supervisor. So if you come from civil engineering, I would not be allowed to teach in civil engineering and advise a master thesis. So you would have to have a professor from civil engineering and maybe have some collaboration. Just as one example. It's really sometimes a bit of a a mess, and sometimes I don't even know it because there are just too many subjects and it's sometimes not clear where the boundary is. Like IMS, computational linguistics, we have a routine mutual agreement, so to say, with colleagues. But also I cannot do natural language in IMS students, but there we have such a close collaboration that's not a problem to do this effectively. Okay, I hope this answers the question. Though it's not black and white, which would always be the nicer answer. Okay, so I hope you know whether you're now in the right place. You have some goal in the distance for what you can achieve with machine learning. And now let's look a little bit more in our vicinity what machine learning means. So especially learning to predict, which often is equated with supervised machine learning. So what are some examples for prediction? So here is a classification task. You get certain kind of emails, and what you get here often is your mail thinks that this email is spam. And I think this was boundary spam. Was not fully spam. But every time that I learn that I'm the son of some prince of somewhere, obviously that's spam, and that should be classified accordingly. So this falls a bit in this direction. So this is automatic classification to help you with your work. And of course, you also see with this problem already what is the practical problem, namely maybe you want to be cautious. Yeah? Maybe you get an email which is important for you and it should not disappear in the spam folder. Right? So, and finding the exact line is sometimes tricky. And but this is definitely one goal that we have. And with some of the methods like support vector machines that we will learn in this course, you could immediately build a classifier. And then you might want to add additional tips and tricks in order to be on the safe side, rather have 10 spam mails too many and not lose a mail that you really care about. What can you predict? You can classify, as I just did in this example, or you can predict a value. So what could you classify? Do you want to send a car to inspection now, or soon, or later? So this would be 3 categories. Quite often in this course, we will talk about binary classification. The point is that you can always go from binary classification, 2 categories, to 3 or 4 or more. Practically speaking, this may be a problem, but from the theory, it's often not that different. Or what disease is it? So typical medical classification, you have certain symptoms. Based on the symptoms, what kind of infection is it, or is it an infection at all? Like, is it a viral infection, a bacterial infection? Should you give antibiotics or not? Is it malware, what you observe on your computer? Yeah? Is it a certain kind of virus, or is it actually some software that you want to have? Stock market predictions. Of course, people try to do this. It is a little bit a problematic area, because the stock market also, to quite some extent, is rather erratic and lives based on outside influences that you cannot know about. And you must be very clever to really make advantage from it. But such advantages have been found with machine learning. For example, a long time ago, people found with machine learning that the traders wanted to close their business on Friday afternoon. So what did they do? They left all the uncertain positions. They wanted to have a quiet weekend, no disturbances, yeah, no emergency calls. So on Friday afternoon, they closed all their risky business and sold them. And on Monday morning, they went into this risky business again, if it seemed likely to succeed. And people found this with machine learning. And then when you know about this, what can you do? When people sell on Friday afternoon, the stock goes down. You can buy and to resell to them on Monday morning again. Of course, it's not worth if you have only 100 euro to invest, but if you have 100 million euro to invest, you can leverage nicely. Yeah? Now, of course, once this is found, there is no value in it anymore, because then people know it and counter-react accordingly. So there are such kind of information to be found. Simply predicting whether we'll go up or down is almost no chance. I mean, most predictions are like, it will behave the same as yesterday, yeah? Like the weather forecast. You already achieve a good rate. If you just say the weather tomorrow will be as it was yesterday, you make it 70% correct without investing any effort. And stock market is a bit like that. What can you predict? Word forms in a text. What you have in front of you, is this a proper noun or is it a name of a company? Of course, some of you may use some software like Grammarly or so that tries to predict whether something is written correctly. Yeah, how good is a move in chess? Win, hold, or loss? Or you can predict sometimes even some of these problems with a regression. So for example, you could ask this question, how good is a move in chess? By predicting some value that you achieve with a certain move. Right? Sometimes chess players think a pawn is worth 1 unit of value, and a horse is worth 2 values of unit. And so you can, of course, try to predict whether a certain move brings your success around a little bit more, maybe even just a tenth of a pawn closer to winning the game. How to steer the car, that's already what I mentioned. When to buy a stock, at which point, that would be another kind of regression. So you see, sometimes the question whether you do regression or categorization is a reformulation of the problem. And you can formulate it sometimes, not always, in the one or the other way. The question is sometimes what is more natural, what brings you better value? And this question, what brings you better value, does not come from machine learning, but it comes from understanding your business. With business, I mean, it's a very far sense. Understanding medical classification is also kind of business, and you can work for a non-governmental organization, and it has some objectives, some goals that you want to reach. That would be the business that you need to understand for that NGO. So you need to understand actually the application in order to see what your problem is. The list is endless. Right? So what is classification? Given input data, what you try to do is you try to learn a prediction machine. So when we say, what is the input? The input is data, and the output is this prediction machine, this classifier. So for supervised machine learning, the output is an algorithm. So let me show you a simple example. This is a made-up example, but it would be a typical database, only that a real database would not just have 13 entries, but a few million entries, and it would not just have like 5 columns, but it would have 100 or more columns. But let's look, I mean, that's of course a problem. Always in teaching, real data is always more complicated than what we will have in any of the examples on the slides. But let's look at this very simple example. So what could you do? You could try to learn a prediction machine. So you could, for example, and what you do here is you have your description of the data, and you have one specified output. And in supervised machine learning, you provide a target category that you try to predict in the future. And so from these examples, this is some shoe size, some price, and some color, you predict something stupidly simple, like with whether something is cheap or expensive. And of course, a very simple rule that you could learn is if color equals blue or price less than this, then it's cheap, otherwise it's expensive. This could be the output from such a training process. And this is a small algorithm. And this is not even necessary. I mean, for this example, it's unrealistic. But when I took my first machine learning class with Pat Langley, the one who later on, who had before created the UC Irvine data set. Machine learners always look at many data sets to test their algorithms. And that's where machine learning started to make progress when, with that UC Irvine data set collection, people had data to try out what the algorithms did. And that started this whole field of collecting data. And now collecting data is a big thing in machine learning and has its own papers in the big conferences. And so what Pat told us was they had one application that was a printing machine operating at high altitude, Colorado or something like that, 2,000 meters. And they really had problems with the printing because you had to turn some knobs that influenced the viscosity of the printing liquid and was influenced by the temperature and by the humidity. And they always kept on problems. And then they provided examples where it worked, humidity, temperature, viscosity, and where it didn't work. And instead of expensive and cheap, they had worked or didn't work. And the outcome was a rule like this. And the outcome they just printed out and put it on the machine for the operators of the machine to turn the knobs accordingly. If the humidity was like this and the temperature like that, then turn the knob on whatever, right? And this can be, in one extreme case, the outcome of a useful and successful machine learning algorithm. Okay. Now, what I want to convey to you here is, when you receive such a problem, the first thing you need to do before you use a particular algorithm, and given that you have such a target, you need to think about the data. You have to look at the data, inspect the data. Don't do anything before you have not inspected the data. And what are the things that you should inspect? By the way, side note here, very often in classical machine learning, so classical I would say, data that works on relational tables as they come from a database. And the more recent ones is more often working on text and on pictures or movies, etc. But still in the industry, learning from data, learning from tables is still very significant. And sometimes you have the mixture. Of course, you may have text inside of database entries. So, the first thing, of course, is to understand your data. What data am I given here? You have to understand what should you predict. I mean, here I tell you, you want to predict this. Maybe it's not so clear when your customer tells you he or she wants to learn something. So you need to even think about, does it make sense to predict it? And some things also don't make sense. For example, right now you can buy software that claims that it looks at videos of you, of applicants, and then decides to pick the right applicants. And this, in my eyes, is complete nonsense. I mean, you can buy the software. It will do some decision, but based on how it does its decision is not, I would say, not even moral practice. It's one thing, and it's not really even effective. It will pick up on something and do some decision, but you will not really know why it does that. Then, what do you have to think about? You have to think about your data. Data can be nominal. So, for example, color in this example would be nominal. That means you have different categories, like black, red, blue. There's no ordering between them. It's not that black is better than blue or better than red or something like that. Well, I know some people for which black is always the best color, but that's a different story. So it's nominal. There's no ordering in that. Other data is ordered, like shoe size is ordered. 3 is smaller than 4, 4 is smaller than 5. So when you have the shoe size, you can take this ordering into account. When you have color, you cannot really take you could do an alphanumeric ordering, but it doesn't make sense, right? Why would you want to have alphanumerically black before the others? Or that doesn't make sense. So for shoe size, it makes sense. I mean, the smaller shoes have less material. Yeah, so there is some inherent reason to order it. And of course, price is not only ordered, but it even has interval scales, which means that you can double a price. Yeah. In theory, you can, of course, halve the shoe size of 6 and you end up in 3, but again, that's not a meaningful halving operation, because what do you do with such a shoe? Yeah, a half shoe you cannot really sell. You can still buy something with half of that money. So in some scales, ordering plays a role, and if you have differences here, if you have €6 difference here, and you have likewise €6 difference somewhere else, I'm not sure whether that's available here, then these are the same €6 difference. When you have one shoe size difference here, how is this the same or different than the one shoe size difference there? Yeah, the shoe size difference doesn't really matter. Only what matters is the ordering. So understand your data, whether it's nominal, ordinal, interval, and you need to be able to work with encodings for these different types of data. I mean, obviously, a price you would naturally encode as a floating point variable. Yeah, for a nominal, there are different ways to encode it. For example, you could have an entry that says black, yes, no, red, yes, no, or you have it like here, but you then later on for your algorithm have to put it into a format that the algorithm can accept. Many algorithms, like neural networks, only accept numbers. If you only accept numbers, what do you do with black or red or blue? You have to do something with it. Data can be useless. In this table, here you have an ID. This is like a product ID. Why? Do you have an idea why this product ID is useless? It doesn't really describe the data. Is this clear to everyone? Why does it not describe the data? It's arbitrary, exactly. I mean, of course, you use it to access a particular entry, but other than that, it doesn't matter, right? There are no groups. Of course, sometimes this is only half true. Take your immatriculation number. Your immatriculation number is somewhat arbitrary, but depending on where on this scale of immatriculation numbers you are, we can approximately see in which year you've joined. So, yeah, probably I would still not use the immatriculation number to work with such personal data, but there you might even have a little bit of semantic information in it. The question, of course, is also, what is your semantics? Do you do something useful? I mean, this always depends on the task. Sometimes values are missing, like this entry is missing. You don't know the shoe color here. Sometimes missing data may give you additional information. Yeah, it's quite common. Customer call centers, they record your data, and then people refuse to give their birth date. What happens very often then actually is also that the user interface forces the call center agent to enter a date. What do the call center agents do? They invent a date. And just to be able to proceed, because they are basically paid by how many calls they take, right? And whether the data is of high quality is not such a big matter to them. Sometimes they agree, let's always pick the 1st of January 1931. And then every call center agent knows, oh, 1st of January 1931, that's not a real date. But it has just been filled in order to be able to continue with the data entry. And then you look at your data, and then 10% of your people are born on the 1st of January 1931. Right? And that's why you need to look at your data. You need to observe what is the distribution of data. Do you have such spikes at certain places where, I mean, you wouldn't expect that 10% of your customers are born at that one day, right? Or it could be several dates if they were different call center agents. Things like this happen. Sometimes you have outliers. I'm not sure what does this. I mean, here, maybe this price is somewhat of an outlier here. I also like to give this example of what would be the average salary here in the room. I don't know, maybe €1,000. We take everyone here in the room, divide by the number of people in the room. We have the average salary, okay? Something like, I don't know, €1,000, I don't know. Now, Bill Gates enters the room. Average salary skyrockets to several million. So clearly, this would be an outlier. And doing a lot of data analysis with now a new average salary of $1 million per year is not very useful to analyze the people here in the room. So you have to remove these outliers before you do something meaningful. Categorization predicts one of a finite set of categories, often just two, true and false, yes or no, but can also be multiple ones, tries, or whatever. And regression predicts values from an infinite set of numerical values. What would be a good price, for example, could be a prediction. How much should the car turn? We can also look at the representation learning. And very simple representation learning could be just to cluster the data. What you see here is exactly the same data as before. And before, we picked this, cheap or expensive, as a target category to learn. And now we take exactly the same data and give it a different task, namely to learn a representation in terms of give me two classes without giving a specific target category. So you try to formulate clusters, and the clusters may consist of cheap products or black products or things that have a lot of commonalities. Again, you have to think about your data, and in this case, maybe the data itself is the same as for a prediction task. And what you have to think about here is what makes items to be more like each other. This can be a very difficult question, and one that also has no objective solution. So the problem when you try to find in an unsupervised manner without a directive structure, you may end up with very different results that all are somewhat correct. Because here for the shoes, you could try to cluster according to the pricey shoes and the cheap shoes because maybe they are in different stores. Or you could have children's shoes and adult shoes because they are different departments in the shoe store. So, and of course you could even do both. You could have a store for expensive children's shoes or cheap children's shoes. So it is a really underspecified, mathematicians would say an ill-posed task, as the result is not quite clear. And what you typically do is you look at the data, you run your algorithms, you interact with the business owners to understand what the problem is and whether your results matches the problem to some extent. And the algorithm here comes with a bias that decides also about the similarity. You will hopefully see this later, not now because they would have to go into more details. That's not what I want at this point. But the point is, there is no absolute truth, and yet the algorithm decides. And this, of course, is true for all of machine learning. Often there is not the one solution, and the algorithm decides. Yeah? We currently write one paper on model multiplicity. A model multiplicity refers to the effect that whether it's supervised learning or unsupervised learning, you can have different models with equal quality assessment that decide differently. And we will maybe see this more closely when we look at the evaluation of algorithms. Okay, here would be, for example, a compact pattern would say, okay, we have two groups. We take two extremes, ID8, that's a very cheap product, and ID10, that's a more expensive one. And then we just pick the ones that are similar to this cheap one. These are 1, 4, 5, and 12. And then we have 10. All the blue ones are similar to this ID10. So these would be two groups that an algorithm might found. And here we picked that it's two groups. We could have picked that it should be 3 groups or 4 groups. So also what you give to the algorithm as a task can be very, very heterogeneous. And even knowing whether it should be 2 or 3 or 4 or 5 is a challenge, and there is no absolute answer. Here's another way of having a compact data pattern to describe. Okay, just I would say maybe even, last 2 slides. What do we see here? Let's start here with supervised learning. What do we have here? We try to learn a classification engine. What do we give here as training data? We give x's and y's. The x's are represented typically, and that's what we will do during all the lecture, in a vector space. When I put a vector space on this screen, it's of course a 2-dimensional vector space. If you don't know what a vector space is, after this lecture, go home and look it up, right? Because that's absolutely necessary to know. So I show it as 2-dimensional space. In reality, typically it has hundreds, thousands, even millions of dimensions. And each point on this vector space represents an object. And then we have for each object, which is described by this place in vector space, a labeling. And the labelings here are A and B. And now when you're given this task to learn a classification engine, and you have these positions for A, and you have the classification according to these y's. The y's are either A or B. You know for each point whether it belongs to the one or the other class. And now what you try to learn is how to distinguish these 2 different groups of A's and B's. And I mean, here we have done a very stupid thing. We have drawn a rectangle here and a rectangle there, and they are not doing so bad, but they leave some out of the picture. And what happens basically always in realistic data is also that you are not able to fully separate the 2 kinds of data that you have. But that's what you try to do. When you have clustering, you get maybe the same x's, and you try to find out which objects are like other objects. And in a vector space, this means which objects are close to each other. So these 2 are close, and these 2 are far away. And then you try to describe these objects that are close to each other in this vector space according to some metrics, and you have to define the metrics. And then you get some result. And one thing is sure. What is sure is that your algorithm will always deliver a classifier, and it will always deliver a clustering result. One thing is not sure, that it makes sense. Your algorithm always delivers something, but whether it makes sense, this is something you have to check. And this is, to understand this, that you have to understand what is the task. You have to understand whether it makes sense, what comes out. This is a core task. So much for today. We'll continue next week and have a good time in your first lecture week. See you next Monday.